This chapter starts us off talking about the tools of astronomy. And astronomy is one of those subjects that people tend to just love. I think because outer space in general is so distant and we know so little, but it's so dreamy and beautiful that it's something that's very endearing to people. And then, of course, like thinking about traveling up into space is just so fun and interesting that people just love this topic. Um, so, one of the ways that scientists derive a ton of the information that we get from space is by using the light that they collect. So, specifically, all light is part of the electromagnetic spectrum. And if it wasn't for electromagnetic radiation coming off of most of the things in space and in the universe, then scientists really wouldn't have nearly as much information that they do about space. So here's a picture of the electromagnetic spectrum, and it deals with light in various wavelengths and frequency. And frequency is like the speed, and wavelength is like the distance from the top of one wave to the top of the next wave. Or you could say the trough, the bottom of one wave to the bottom of the next wave. So really long, slow wavelengths are like on this side with like radio waves. They're long, they're slow. And then gamma rays are very high energy and fast. So what we can actually see is this tiny little sliver here, and it's very small. It's in between infrared and ultraviolet, this tiny little piece called visible light, the visible light spectrum. And it's so small, and they expanded it here, and it's basically all the colors of the rainbow that we can essentially see, which is very, very small. There's all these other types of light around us that we just can't even see with our eyes, but it still exists. And this is something that's amazing to me. In fact, insects tend to see in the ultraviolet spectrum, and which is way bigger than our sliver that we can see. So insects can see, I don't know, what is this? How many magnitude bigger is this? 10 times more? Something, a spectrum of light that is far larger than what we can see. So to pick up this light, we use the most common tool that astronomers use is telescopes. And telescopes allow us to observe wavelengths beyond what the human eye can detect, and they allow us to collect electromagnetic radiation from faraway objects that we can't see, but this can be recorded for us to look at and to study. So there's two different types of telescopes, and you are going to need to know the difference between the two. One is called a refracting telescope, and refracting telescopes rely on light going through different lenses so that you can see what you're looking at. So that's refracting. Reflecting, just like you would look at your reflection in a mirror, reflecting telescopes use mirrors and a little bit of like a lens, but just remember, reflecting has mirrors, refracting is just using lenses to help you to see. So that's the difference between those two. So telescopes can be really, really expensive, and huge, massive telescopes to see things really far away or with extreme clarity are very, very expensive. So scientists are forever getting clever with how they use the technology and the funds that are available to them. One of the ways is to use multiple telescopes that are nearby each other to focus on one object and make kind of a clearer picture of what they're looking at. And that combined power, the process is called interferometry, and the combined distance between the two telescopes basically is the magnitude of the overall image that you can get. So by spacing out the two telescopes and focusing on the same image, you can get a much larger view than what you would get with one telescope alone. So that's why you would have a bunch of these on one mountainside, which brings me to where are telescopes placed? Telescopes are generally placed in places with really low light, so there's not as much interference, and really high on mountaintops. So they are usually remote, hard to get to, and of course expensive to get to those places. So sometimes scientists, actually astronomers, will send stuff into space. And they do that because then they can get away from the Earth's atmosphere where there's light interference, where there's radiation interference. You get blurry images. There's ultraviolet radiation, x-rays, gamma rays, lots of things that get in the way. So if scientists can bypass all of that by shooting things up into space, either people, satellites, telescopes, then they can get all around that, and they can get much sharper, more visible pictures without all that interference. So if you want a picture free of interference, you put your telescope up into space. And the last thing that I want to mention, and this is so awesome, is that there is a ton of what's called spin-off technology. These are technologies that we all benefit from because of space exploration. Because astronomers are studying space, we get a bunch of products that we wouldn't otherwise have. So this is just NASA's Jet Propulsion Lab. There's other space organizations that have inventions, but camera phones came about because of NASA, and scratch resistant glass. And you can read about each of these. This is just JPL's infographics, and it's called 20 Inventions We Wouldn't Have Without Space Travel. So CAT scans, LEDs, and you can see why they invented this for space, and then how we use it on land. So land mine removal, athletic shoes, foil blankets, water purification, dust busters, ear thermometers, home insulation, jaws of life, wireless headsets, super important, memory foam, mattresses, freeze-dried food, certain types of smoke detectors, baby formula, artificial limbs, computer mice, portable computers. All of these things were invented for space, that if we hadn't put money towards those programs, they wouldn't be around. So a lot of times people say that space travel is a big waste of money, but it's actually the program and the problem solving is contributing to a lot of greater knowledge that we use here on Earth.